Thank you for the introduction. I think this is like a short caveat, but I think it's surreal that I got to get introduced by someone who went to space. I still remember I was in elementary school. Um, every teacher just had the students just look up at the TV and just saw you go up there. So I think it's an honor to be introduced. Can you guys all see my screen right now? Okay, cool. So yeah, my name is DJ Lee. I am a PhD student at Purdue. I work with Roger Waynes, um, and I do everything on libs. So there are two big parts in our lab that we do. So we actually, the first part is the science. So we actually already have two libs instruments on Mars. So we actually, at Purdue, we have a operational room, and the grad students actually get to choose what kind of rocks we're going to analyze. So we're in the forefront of the actual analysis. The second part of of our lab and also my PhD project is to actually develop a new second generation LIBS instrument. So I'm going to just talk about the two briefly, and I think the audience is a mixture of engineers and scientists. So yeah, I'm just going to do I'll try to be really quick. I only have like 30 minutes, right? Yeah. Yeah, so just you talked about Antarctica. That moment when I saw you go to space, I was like, okay, I'm gonna do that. Like, I really thought that we're gonna send hundreds of people there. When I graduated from high school and went to Seoul National University, I found out that we're not gonna have that much astronauts, especially in Korea. And then I found out this like the closest thing we can do is to actually go to Antarctica. So the work that I did in Antarctica is actually it was still planetary science. It was more about modeling. So on Mars, there's also on the poles there are glaciers and there are trough migrations. I'm just gonna go through that, but so we did some modeling, the same thing we did um, in Antarctica, and then compare that to Mars. And then after that, I joined Purdue Planetary Spectroscopy Lab. Right now, so before I talk about the actual instrument, so what is LIBS? LIBS is actually a really common instrument in analytical chemistry. So basically, a laser shoots a sample. It could be anything like a rock to even fluids, plasmas, even even atmospheric data. But you shoot a laser, it creates a plasma, and then when that plasma decays, it emits lights that's specific to the elements that's present in that plasma, and that's how we do chemical analysis on it. What's pretty interesting is that we already have four LIBS instruments that are on in space. Two, which ChemCam and SuperCam, which is operated on with NASA, but also Mars Code A, which was run by the Chinese Space Agency, and also the Chandrayaan, which is the only LIBS instruments that went to the moon. Um, Chandrayaan actually did not have a focusing mechanism, so after the launch, we got the initial data, but they did not yield real scientific evidence on anything because of the lack of focus. But for the Mars Code A, ChemCam, and SuperCam, they provided just robust data sets on geochemical analysis on the Mars surface. Um, and especially, I'm going to talk about ChemCam and SuperCam. So the PI Roger Waynes is my PhD advisor. The first time when we chose this is because the initial scientific initiative was to see if we can find potential biosignatures. Um, and because of that, we focused on deltaic features that are on craters. So craters are natural, we can say it's like naturally excavated. So even if we don't have to drill through, a crater is an asteroid that went on, it actually dug up the actual surface of Mars. So as we traverse through it, we can actually analyze stuff from the really bottom, from the old stuff to all of the new. And this was really advantageous for ChemCam and SuperChem is because as we traversed and did a lot of other analysis and other instruments, Libs can do the actual background chemical analysis, and that's where we got the big data sets that we have. So, what I'm showing here is the actual data sets that we've achieved already. It ranges all from 4,500 depth all the way to 4,200. So that's like over 300 vertical meters. which is a pretty significant depth profile. Not only that, it really shows figured out a lot of scientific stuff that I'm not going to talk about today, but it showed that we can actually be versatile in very different mineralogical features, and also it yielded really good geochemical data. So this is actually a time lapse of the actual laser penetration on Mars. Why we say this is very versatile is because there is no sample prep. So we can just shoot the laser in situ, and as you know, Mars is very it's like a red body, right? It's very dusty. The laser actually ablates the dust on the regolith that we want to target, and we average up to 2 to 5 shots per point. But over here, we tested up to 100 shots, and you can see that the laser actually penetrates through the regolith and it digs in. So you can even have a depth profile in the same regolith itself. Um, this is the first SuperCam Lib spectra that we'll get. So the data set ranges from 240 to 800 nanometers wavelength. So we can go from ultraviolet all the way to visible near infrared. And it is very sensitive to the light elements, but also all the major elements that we expect to see on Mars, and also on the moon, because what we were focused on Mars and the moon is quite different. On Mars, as I mentioned before, it's mostly biosignatures, but on the moon, we talk about like helium-3, or in permanently shadowed regions, we talk about icy rocks or stuff like that, and those are really hard to get from other instruments like the SEM or the X-ray XRF. But for libs, we're really sensitive on that light element, so I would say that's a really big advantage. So we can use the exact same heritage we're using already on Mars, and we can just apply that to the moon, which is I'm going to be talking about on the later pages. This is one of the I just wanted to shout out just like a very recent paper that came out that our team collaborated with. This is a potential biosignature that was found in the on the Mars uh, it was the late angel formation is what we call it. You can see uh, we shot consecutive shots, so it's not just like a single shot. It's like a map of the actual surface on which we want to get. You can see that there are increments inside, which is thought to be bacterial, at least in on Earth. The only way we can actually find these features of bacterial. So that's why we say because of the nodules and the focus of the actual elements that we found here, we say it might be a potential biosignature. But yeah, we couldn't have got this results if it were not for the XRF, but also the libs instrument. So just to sum up, what we do on Mars is we get a high resolution surface picture. We choose what kind of outcrops we want to shoot on, and then we shoot our libs. We analyze the elemental composition, and then yeah, we do fun science. I'm just gonna go through. So what the students, including me, the PhD students do is there's already automated NavCam images that are acquired through the actual camera that is on the SuperCam. And this is of course shared all through all the instrumental teams. What we do is we recommend what kind of rocks we want to shoot. Sometimes it could be a weekly mission, it could be an yearly, but there's a theme in every mission subset. So when we let's say we want to look at the biosignatures and the leopard spots, so we just try to pick as much rocks that we want that look like the scientific features that we are themed in, and then we have scientific discussions in our team. These data sets are open to public. I think they're closed for like 3 to 6 months, not sure, but after that, not only me, but like the whole public can do a really good science with it. So if you guys are interested, you can just go to the NASA data set and just do science with. Um, I'm just gonna go through. I wanted to talk to you guys about also the libs on the moon. So, what I found out, because most of my research was on Mars, but now it's shifting to the moon. What I found out is that on the moon, the objective is very different. So this is the Lunar Institute Research Utilization Planning that NASA has right now. There's the global resource identification. These are done by orbital satellites, which we already have a lot of data sets. And the next step will be local resource exploration. What we found out on Mars is that the analysis done on orbit will very differ if we actually land and do LIPS instrumental mapping. I think that's what we expect, and because we're trying to find for NASA, the biggest priority is, of course, because of the Artemis mission, is ice, so H2O. It's signatured by uh, hydrogen, which is a light element, which is very hard to find with other instruments. So that's why we need libs. And if we're gonna, the next step is gonna be local resource exploration. I think there's a pretty big chance that we're gonna have libs on the Endurance mission or even the actual Artemis astronauts just having handheld libs and just shooting rocks at it. But this kind of like verification, I think, is really opportunistic for us, is because the next step is the local resource exploration, and it's gonna be it's gonna be focused on light elements like helium and hydrogen, and which is gonna be really sensitive with libs. So I just wanted to spot that out, and just gonna shoot. So, apart from the actual operations that we do on Mars, I told you guys that we actually do new instrument development using the libs. So this is called Micro Libs. It's a joint project with the French Space Institute and Los Alamos, and it's going to be a very small, modular, and versatile laser. It's going to use the same. I'm sorry. Uh, It's going to be a very small Libs instrument that's going to do consecutive shots, but it's going to be a more coarse-grained, more fine 2D image of the workspace. It could be regolith, it could be permanently shadowed regions. This is like the basic development that we are. We're already in TRL 5 and 6. It's going to be about 1.5 kilos, which is about 5% of the weight that SuperCam or ChemCam is weighing right now. And it's going to have a scanning mechanism. So without the rover moving, it's going to be on one spot, and the scanner is going to do the actual mapping. And of course, the combined spectroscopy and the miniaturized laser is going to be the same technique that we use on SuperCam and ChemCam. We actually want this to be on various missions. Right now, we're interested in the Endurance mission, but also we started working with actually with the Korean Space Agency, which I and which we actually got to go to Korea like last week with my advisor. They're very, I think CASA is very interested in the in situ space resource exploration, where Endurance is focused more on the hydrogen and helium. I think Korea is more interested in the Crete region, the rare earth materials, which is also it might be hard because of the spectroscopy sensitivity, but still it is plausible for libs to catch out those kind of elements. So yeah, I just want to point out libs very versatile. We want it on future missions. I think I have a few more. What's interesting about the Libs plasma that is produced by the laser is it is very sensitive in the atmosphere that it's in. So we found out that having Mars atmosphere, which is 1% of Earth, is actually more advantageous for the Libs plasma to be analyzed, because on Earth the atmosphere pushes down the plasma too much. The plasma is so small, whereas on Mars it's like just the right amount where the spectroscopy just catches it with the timely manner. On the moon, of course, it's going to be on vacuum, so it's going to be really hard. Those analysis are what we do on our lab. We've already done so this is just like a program that we that I developed. We're gonna do mapping on the moon. We have a lunar chamber. We actually did some mapping. This is the results we actually got last week. So we actually verified that even though the vacuum makes the plasma just vanish so fast, the spectroscopy that we use, the same sensitivity that we use on SuperCam we have on our lab actually catches out all the data that we wanted. So this is not just a simple like data set. This is all calibrated. So we have all the weight percentage. We have standards that are pressed into pellets. We put it into a lunar chamber. We shoot the libs on it. We do like 100 shots for 100 samples. We get that out. We actually have a lunar meteorite. We put it in the lunar chamber. We did some mapping. I think this was, I want to say 30 by 30. So it's 900 points. And we found out without doing any other like algorithmic like programming stuff, just by raw data, it came out pretty good. So we were actually surprised by this, but this is going to be published next week. Not sorry, next week, next year. And yeah, I think we're gonna have some future LIBS instruments on the moon as well. Um, yeah, I think that's time. Thank you. Yeah, and this work was funded by NASA because of grant. Um, Thank you, and I'll get your questions.